Today I'm going to talk about something that I think has really informed how I approach programming, and that is really that types and static types can be as much a tool for better design as they are a tool for correctness. And but to get into that, I think we need to start by figuring out, what do we even mean when we talk about code design, right? And this is one of those ideas that I think isn't particularly well defined. There's a lot of different books written about programming that touch on various aspects of design, and people take a lot of different approaches. But for me, I found recently, I found one book that helped crystallize the way I was already thinking, which was this book, The Essence of Software, where the key idea, for me at least, was that when we're designing software, we have some set of sort of concepts in our mind to represent what we're trying to do or how we're thinking about the system. And trying to do a good job of designing these concepts and having code that can map to those concepts is a way to design better software, both from the user's point of view, but also from the programmer's point of view. But to do this, let's throw together a very simple mental model of how we can approach programming. And one way to approach programming, and this is something I've actually seen when I mentor people who are complete beginners, is this sort of very direct approach. You just sort of write the thing, right? You write some code, you see if it works. If it doesn't work, you change it. And the problem with this is that you quickly end up with code that sort of works incidentally, right? Like it happens to do the right thing now, not because it's designed or built in a way where the right thing is the natural result, but just because you've got it to line up at this specific moment in time. And as things get more complex and people get more experience, right? It starts being impossible to just sort of write code without thinking at all about how to sort of simplify what you're doing and how to come up with some sort of abstract concepts that let you tame the amount of details that you have to deal with. And so the basic model of how to approach programming is something like, you have the world or whatever you're doing. Then you have some kind of mental model that some ideas and concepts that you're using to understand the world and to understand what you're building. And then, finally, you have the code, and ideally, the code should be informed by these concepts. However, sorry. Yeah, and one thing I like about having this very clear separation between concepts and code, right? Because at the end of the day, there's always going to be a difference between the sort of idealized ideas you have in your mind, which might be a bit fuzzy, but also more adaptable to deal with the sort of infinite complexity of the world. And then this very specific code that you've written, which might be overspecified or it might be a bit off, is that this model lets us separate the ways in which we can have code problems or technical debt and the ways in which we can improve the code base. For example, some problems are going to be purely about the code. They're not really about the design at all, right? Maybe you just need to run a linter and clean things up. Other problems are going to be at the level of the sort of conceptual design, right? Perhaps the way you're thinking about something doesn't really make sense. Like the concepts might be inconsistent, they might be incoherent, they might just be too complicated. And I've actually seen a lot of systems where the fundamental design wasn't a problem because the code was poorly written, but it was a problem because it was written based on some set of ideas that was not very well thought out or not really fit for purpose. But actually, I think there's an even more subtle and I think more important way for things to go wrong, which is in sort of the distance between, reality and your ideas about it, so your concepts, and also very importantly, the distance between the concepts that you and other people use to think about the code and the code itself. So like, how easily can you map from the specific artifacts and constructs in your program to these ideas? And when you have this kind of mismatch, right, you get a lot of bugs that are very distinctive in the sense that fundamentally they should not even be meaningful, right? But they happen, right? I found a really cute example on Reddit at some point, which was this idea about how you could accidentally delete all your files with rsync. And the story goes something like this, right? When we run a command line command, we have this idea of how it works, right? We have a command. Then we have these command line flags, which are little toggles that tell the command to do different things. And then we have the arguments to the command, the file paths. They represent files, right? And there is a qualitative difference between flags and files, right? Flags are controls, and files are inputs, right? Unfortunately, at the code level, the way Unix sees this, and the way the program that gets the command line argument sees this, is basically a list of strings. There's a bit of a special case for the command itself, and everything else is just undifferentiated strings. So when you're writing some command and you use a little shell glob, right? As a person, you're still thinking, hey, this list of files is going to be a bunch of inputs to my program, and it's going to copy all those files into this other directory. But what happens, right, if somebody makes a little directory and it creates a file called --delete, right? It reads the file name as a flag and deletes the code. And the problem here is that in some sense, this isn't really a problem with rsync. This is a fundamental design issue, because there's no way within the system for rsync to know whether some random string was meant to be a command line argument or was meant to be a file path. We just don't make that distinction in the code, even though obviously there is a very important distinction there kind of conceptually. So that's a good example of bad design. But the question is, well, so where do types come in, right? What is the point of static types? And I kind of stole this title from a really good talk title by Connor McBride, which is, what are types for, or are they just against? And the question I have is sort of like, do we need static types for good design? And I think there the answer is no, right? Like any sort of abstraction will let us build up good design in our code, right? So if we don't strictly need types for design, right? Like what are they going to be for? And I've seen kind of 3 different models that people have for how to think about types, right? There's the model of types being sort of bug preventers. There's a model of types providing code structure. And then there's the model that I'm kind of advocating here, which is thinking of types fundamentally as a sort of a tool for thought and a tool for design. Now, if you're just thinking about types as a way to catch mistakes, it inherently means you have a kind of a limiting view of types. And I found this often comes from languages that have very limited type systems, or maybe from people who really prefer dynamic typing, right? This is where people say things like, well, I'm never going to confuse an int and a string, so what's the point of types at all? And the problem with this view is that if this is the approach you take to static types, they'll only ever be useful for problems within purely the code and not any of the problems in the design, right? They won't help your code better match or track your concepts, and they won't help the concepts themselves, right? So that is very limited. Other people have this view of types as sort of interfaces or modules or modularity, so ways to organize a large code base. And that is, again, substantially more than just preventing, confusing 2 arguments or something. But there's still kind of a limit to this view in the sense that the types are kind of still seen as separate from the core of the code. And this is something like where in Java, I think you can, and I think a lot of people do. Imagine being able to program in Java just with no types. And it would feel kind of more or less the same, except you don't have, type errors, right? And I think this is where a lot of discussions come up, where people treat, static versus dynamic as like a single bit, like a binary question. And that's because if your types are there to help you get structure, whether you check them statically or dynamically doesn't really change anything. That's that, once you're caring about structure, the types do start helping you with design to some extent, because you can use the types to kind of push the rest of the code base to stick to a pre-planned structure, right? The types form the skeleton, and if you set the skeleton up correctly, it can help keep your code aligned with the conceptual model that you want. However, as I was saying, for me, and I think for a lot of people who use kind of typed functional languages or languages with more expressive type systems, the type system itself becomes a tool for refining and actually changing the design of the code base, or even changing the way you think about whatever you're doing. That is, changing your actual conceptual model. And with that approach, you can really see types kind of becoming a qualitatively different tool than kind of the first two views. So as I was saying, we have these three views, and I think the first two are maybe more common, but it's this third view of types as design that I think is very interesting. But that brings us to an important question here, which is, well, why do we need static types? And I guess if we pop back to these three types three views of type systems, right? If you just care about preventing bugs, then static typing helps a little bit, but you can do tests and you can catch errors at runtime. That's fine. If you care about code organization, well, you can still have classes and modules and whatever else you want. And again, like it might be nice to check statically, but it doesn't give you anything fundamentally new compared to having runtime checks. But if you're looking for design, right, well, that becomes a different situation. Because what do we want from a design tool? Well, one of the biggest things is we want to be able to use that tool when we're designing. And that also means that we want a tool that, where the computer can give us useful feedback, right, and it can do useful work before we have working code, right? Potentially before we've written any kind of real code at all. And for that, you really do need static types because, to do things with the dynamic types, you really need to run the code. Otherwise, the computer can't help you much, and you're just thinking in your head. And the other thing that is also very relevant for static types specifically is that they give us a different way to abstract over the systems that we're building, right? Like, as programmers, I think we're all very familiar with building code abstractions that abstract over implementation details, right? So information hiding. But types actually abstract a little bit differently, where you can use types to provide a kind of a simplified and kind of intentionally limited model of how the program actually runs. So you're sort of hiding details about the actual semantics of your code, right? So that you can reason about them in a way that's a lot easier than dealing with all of the possible complexity of your running program. And there's kind of a classic way to visualize this, where you can imagine your code running along different traces, right? So you have some input, and then the code runs and it hits different states, and it could really be arbitrarily complex. And for real code, right, there's an infinite number of ways the code could run. And because of the halting problem, because of Rice's theorem, we know that we can't ever fully reason about every possible trace of a program in a way that's precise. And even if we could, even if the program was very restricted, right, the full runtime behavior of even seemingly simple code can be very complex and very hard to keep in your head. So we need some tools, some kind of abstraction that lets us take this very complex runtime behavior and have a view that is simple enough that we can think about it, keep it in our head, that we don't have to overstrain our working memory to figure out what's going on, but is also still capable enough and useful enough to do things with, right? And that's kind of one of the things that type systems get us, right? A good way to imagine it is if we have this very complex set of possible traces, then a type system carves out a simple shape in the space of all possible program behavior that's conservative. So it says, I'm going to cover every single possible way for this program to run, and that's going to include a bunch of possible states and then traces that will never happen. And maybe it'll include traces that are logically a bug, right? But by being conservative, we can get something that's kind of simple, and we can also make this guarantee, this type safety guarantee that, hey, you're never going to see a state or a trace that is out of bounds of what the types guarantee. And so this kind of simplification is the other thing that you only really get with static types, right? Because with dynamic types, all of the behavior and checking happens at runtime, and you're back at dealing with all of the individual possible traces that you have in your code. So yeah, the reason that I think it is specifically static types that are so good as a design tool is because they give you this kind of fast feedback, right, even before you have working code. So you can write a bunch of Haskell, not fill in any of the definitions, but see, like, do your type definitions fit together? Do your functions do what you expect them to do, right? And in fact, that's often how I start programming. And so you get a bunch of quick ideas, and often you start refactoring before you've written code because you realize, hey, my original approach wouldn't work, wouldn't make sense. And we can do this because, again, the checking happens without needing to run code. And then the types also give us a simpler way to think about the behavior of different parts of our program when we don't need to fully understand all the details, right? But we just want some idea of how things fit together. And this is also where the expressiveness of a type system becomes pretty important, because the extent to which we abstract over the runtime is up to us as programmers, right? We're the ones choosing how precise of a type to write. And so, on the one hand, having more precision lets us have types that are kind of closer to the full behavior. But the problem is that that isn't always a good thing, right? It might make it more precise, but it also makes it more complex. And sometimes this is a problem just because the encoding of your logic in the type system is awkward. But it's also a problem because one of the goals of having types is to have this kind of simplified summary that's easy to hold in your head. And if you expose too much of the sort of real behavior of the program, then the summary becomes sort of insufficiently simplified to keep in your head as easily. And you lose that advantage of having this specific sort of abstraction over the runtime behavior of your code. So I figured we can jump in and look at a couple of little examples. And one problem I've had with coming up with examples here is that it was really hard to find things that didn't require at least a bit of context and background that's hard to supply in a short talk. But one little project I've been kind of working on, I had a friend who wanted to do this little learning exercise of implementing a JPEG encoder. And it turns out that encoding JPEG is reasonably straightforward, but it has a bunch of steps, and you have to do a bunch of different transformations of the original image. And so as soon as we started this, right, the first thing I did was I said, OK, well, we can start by outlining the top-level type that we're trying to accomplish, and then kind of working down, adding more types, right, and writing the types as a way for us to understand how the whole JPEG process works and figure out what the different steps entail and what we have to do. And you can see kind of like the top-level type is something like you go from an image that's in RGB, and that's already giving you some ideas about how we see things, right? Because we're talking about color spaces right away. And then eventually you create a byte string that should be in valid JSON format. And then as we went through it, we'd read up on how JPEG works, and then take the ideas we saw and turn them into types. And I found that this exercise really helped me understand some things that maybe are obvious in hindsight, but that I arrived to faster by starting with this typed exercise. And a good example here is like one of the steps that you do in the JPEG process is after switching to this awkwardly named color space, which YCBCR, you do this downsampling step. And when I started reading about this, right, in my mind I thought, oh well, a downsampled image is just kind of really the same thing as a normal image. Maybe you just like sample some of the pixels. But the key thing that makes JPEG work is that you sample these different channels separately, right? And in particular, the Y channel, which is the sort of the chroma channel, the brightness, you keep 100% of the information, and then you downsample the blue and the red channels. And that is one of the core ideas that sort of makes JPEG work. It's like humans are good at seeing brightness. They're less good at appreciating a little bit more, a little bit less red. And so what happened there is I found that, hey, even just without writing any code yet, in the types I can see that, hey, we can very easily represent an image as just like a vector of some kind of pixel, like some object that represents a pixel. But we can't ever do that for a downsampled image because the different channels are going to require different numbers of pixels. And then because they have different numbers of pixels, they're going to require different sorts of indexing arithmetic, and we really have to be able to treat them separately. And the types not only helped me kind of see this earlier, right, before I got into writing a bunch of code with a bunch of indexing and confused myself and ran into all these off-by-one errors, but also in the code, it kind of made it very explicit when we're going from sort of one mode to the other, and gave me these sort of touch points where to figure out, what kind of indexing do I do. And then another example I have is, for a couple, like last year I was working on this book, which was, it is an introduction to reinforcement learning and dynamic programming, and it's aimed at sort of applied math people. So the code is in Python, but one of our goals with the book was very much to sort of demonstrate code design, but also have code examples, right, that where the structure of the example reflected the structure of the algorithms and the processes that we were modeling. The thing with Markov decision processes is the way they're usually presented sort of in math, it's kind of fiddly. There's a lot of little moving pieces. And the details don't matter for this example. But the point is, it's not done, like it's done in a way that doesn't highlight some of the most salient aspects of what makes a Markov decision process a Markov decision process. And then you also have to have, there's other definitions you need before you get to that one. And the thing I did is, before jumping into Python, I actually sat down in Haskell, kind of sketched out some types for what these things would look like. And one thing that happened immediately was even the simplest version of these types kind of made it a lot simpler for me to kind of see how these things worked. And in particular, if you see the function specifically for like Markov process, unlike the math definition, this version kind of, with the state mapping to this distribution of states, makes it really clear how these things compose. Like, how do you go from a single step to a whole chain? Like, what makes it a process? And then also, and this may be a bit less obvious, but this S to MS construction also just happens to be a really kind of classical way to model automata. And again, like, if you've spent a bunch of time working with Markov chains, I'm sure that thinking of it as a special kind of automaton makes sense. But to me, at least, it was much easier to appreciate what that meant by seeing kind of a simplified representation like this. And then later on, I actually figured out that because we're parameterizing over how we represent the distributions, we don't even have to deal with all this extra bookkeeping around rewards. And in the Python version, this was actually a big headache because we didn't have an easy way to do it. But here we can actually factor it out and have a smaller set of concepts. And again, like, what this ended up doing is the types really reminded me that when you have like a Markov process, you can think about the process as having rewards and an objective function. But sometimes it's a very useful perspective to just see these sort of state dynamics of the system and not worry about the rewards at all. And in math, people are used to kind of seeing the same thing from multiple sides simultaneously. But I think, again, I found it's nice to be able to do that in code. And again, like, it made it really easy to figure out, like, oh, how you go from like a Markov decision process to just a Markov process or something. But I think maybe a better example here is that we didn't, like, these three type variables all actually play a very important role, which is that when you have different reinforcement learning or dynamic programming algorithms, they need different properties from like the actions and the state space and so on. And by having these parameters, we get essentially a single concept that covers all of them. It's very explicit about which requirements you need for which algorithm, but you also don't have to make up distinct names and concepts for each kind of process, right? And I think that's pretty powerful and only works because, again, the types are pretty expressive. So in this instance, right, what did static typing get us? Well, it helped, in both cases, it really helped kind of simplify, but also kind of reify, make concrete the conceptual model we needed to understand the domain, whether it's JPEG and image processing or it's Markov decision processes and reinforcement learning. It let me get some feedback before I had runnable code, right? I could actually see, like, hey, if I do it this way, will it make sense? Will I be able to like run a simulation of this Markov chain if I organize the code this way or this other way? Then as we're programming, the types give us some interactive feedback. We can do this kind of goal-oriented programming where we leave holes in the code and work towards types. And then finally, once we're done, the types serve as a high-level guide to our conceptual model. And my goal for code bases is always that reading the code base should work well as an education in whatever the code is doing. And I've found that types tend to be very good about that. I think a cute example is like, there's this Haskell package called color, spelled with an OU, which also ends up working with its types and functions as a pretty good introduction to color spaces in general. So, once we start thinking in terms of designing our code in this way and using types like this, right? What do we get from that? Well, the first thing is that we can just start practicing, essentially type-driven development, right? When you're approaching something and you're using a typed language, you can sort of first carefully think about the concepts you want your code to refer to and to represent, then design types around that, and then get the code from there. And this is both a very productive way to design and write code, and it's also, I think, more likely to produce higher quality and easier to understand programs. And the other thing is that this is not so much normative as that this is just the way that typed programmers work, right? I saw this study recently, which was an observational study of a bunch of typed functional programmers, and essentially it saw that they did pretty consistently use this sort of type-driven approach. Then at the same time, all of these ideas fit really well into doing things like domain-driven design. And it turns out that while domain-driven design, I think, has this connotation of being very object-y and object-oriented, it is actually very nice to be able to take your sort of domain glossary and domain concepts and translate them into these high-level types, and it fits into your functional world. But for me, at least, thinking about types in this way also really changed the way I think about and evaluate the idea of dependent types. Because originally, right, it seemed like everybody was excited for dependent types only kind of if they really wanted to be able to verify code or prove things that are hard to prove. But what I've realized is that a lot of the times, what dependent types would let us do is write simpler, more expressive types that, on the one hand, are closer to the concept we want to represent and do a better job of expressing the way we're thinking about something. But on the other hand, don't have this sort of complicated overhead of bending over backwards and encoding them in terms of type-level features like Haskell has that aren't really designed to be flexible or to do these things, right? So in some sense, I kind of think that magically moving from Haskell to, let's say, like a dependently typed Haskell might actually lead to a bunch of types getting simpler just because the type system becomes kind of more flexible and expressive, and people can use that not to make more precise types, but to make the types they already have much nicer and kind of easier to write and easier to understand. And then I think this is also kind of a very topical idea because we're kind of entering this world of LLM code generation, right? And if we take a step back and we think about what these new code generators do well and what they don't, right? And today what they do well is they design, they can spew out large amounts of bad code. And honestly, one of the things I'm kind of worried about is that we already kind of live in a world where there's too much bad code, and making it easier to make more of it won't help. But that's the state today. And so we kind of want to take a step back and think like, well, can we have some kind of better tools, right? And no, I'm really saying better tools rather than the better models, right? Because I'm not convinced that there's any easy way to go from the LLM code generation we have today to something that's really good. But I am convinced that there are ways to build tools that let us work at a higher level, right? Have a clean, high-level design that a human came up with and that makes sense and that works really well. And then rely on code generation to actually fill in the gaps and make it all work. And then as a bonus, right, one of the reasons you might want to use a type system for this, or for that matter, like a specification language, is that you can actually get some level of verification and make sure that the LLM isn't just making up nonsense that looks plausible, right? And in my ideal world, at least, LLM code generation will enable us to focus more on design and spend less time on boring code and less time debugging. But I think unless we take an approach like this, it'll just end up spending 90% of our time debugging and then the remainder, well, I don't know. Anyway, yeah, and then ultimately I think this just comes down to something I kind of believe in general about programming tools, and that is, good tools should really help us think. And I think treating types as a design tool is one way to do that. But I think the same principle definitely generalizes. Okay, yeah, and I think that's it.